Welcome back, geometry students. Today we have the incredible opportunity to see and experience the proof of the great and grand Pythagorean theorem. You've known the Pythagorean theorem for a long time, that a squared plus b squared equals c squared. But up until now, you've been simply expected to memorize it and take the teacher's word for it. You're told to memorize it, you're told how to use it, but if you ever asked in the past, Mr. Johnson, or whoever, why is that true? Well, your typical elementary or maybe even middle school teacher is probably not going to know, and they'll say, shut up and just believe it. I don't know. But today, we get to prove it, so that instead of believing it because some teacher tells you to believe it, now you're going to believe it because you, for yourself, have seen the proof of it. Now, if we had a regular classroom setting, this would be required as a quiz. I would show you the proof, we would work it through together. A couple days later, you would take out a blank piece of paper in the classroom and you would write out the proof yourself, thus being able to say that you yourself have proved the Pythagorean theorem. But I think that's kind of pointless to ask you to take a quiz at home on this, because it would be too easy to simply copy your notes. But please try to appreciate the beauty and simplicity of this proof. And at the end of the proof, we'll talk about how to use it, and you'll have an assignment on the Pythagorean theorem. All right, so moving on, I need to switch windows here. Okay, first of all, what is the Pythagorean theorem? There it is. In any right triangle, a squared plus b squared will always equal c squared, where a and b are the legs, and c is reserved for the, what do you call this? It's that H word. Yeah, I heard it. Hypothesis. No, not hypothesis. Don't be silly. Hippopotamus. No. Okay, yes, there we go. Hypotenuse. This is the hypotenuse. How do you recognize the hypotenuse? That's rather important to the Pythagorean theorem. There are two ways to recognize the hypotenuse. One way is, it's the longest side of the triangle. We proved that in a previous chapter. Another way to recognize the hypotenuse is simply that it's opposite the right angle, and you can think of it, as we discussed in class a long time ago, you can think of that right angle symbol as an arrow pointing to the hypotenuse. We'll discuss later, at the end of this video, I hope, we'll discuss how to use the Pythagorean theorem to find missing parts of a right triangle. Before we do that, though, let me show you this. Now, I can't see exactly what you're seeing, so I'm just going to have to kind of go in close and hope that you can see this well. I can't tip this very far, because if I do, it'll fall apart. But this is a right triangle. Okay? And this side has a length of 1, 2, 3 units. See, I told you. It's your fault. You made me tip it up so you could see it, and it all fell apart. I'm going to give somebody detention for that. But Mr. Peer, that's not fair! Oh, be quiet, imaginary student. Stop complaining. Okay, let's see if I can pull this off. Maybe if I tilt it this way, it might work better. I don't know. Probably not. Okay, so this side has a length of 3 units. This side has a length of 4 units. If this side has a length of 3 units, then the square on this side, 3 squared, equals, count them, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 squares on this side. This side has a length of 4, and therefore 4 squared means the area here is 16. So this area plus this area, a squared plus b squared is supposed to equal c squared. And sure enough, if we rearrange this, and can I do this without making a mess? I have no idea. If we rearrange this, this is hard to do without spilling them all over. And let's see, let's put this guy over here. And I'll put this one here. Will this work? If I don't get this just right, then things don't come out right. Let's put him there. Oh, yes, I've got it. That was easy. There we go. And I can arrange them so that those two areas of a squared plus b squared, 3 squared plus 4 squared, 9 plus 16 equals 25, which is indeed 1, 2, 3, 4, 5 squared, 25. So the area of this square plus the area of that square will equal the area of that square, no matter what shape the triangle is. It doesn't have to be 3, 4, and 5. Any right triangle, this area plus this area will always equal that area, guaranteed. We're about to prove it. So let's dive in. Oh, let's see, where is it? Next screen, there we go. I do to streamline things and make things a little bit simpler, especially when students are required to memorize the proof. I do take one shortcut. The altitude here should not be part of the given information. My first step in the proof should be to create that altitude. But I've always taken the shortcut of just allowing the altitude to be part of the given. For the purists among you, that would bother you. So if that bothers you, you can rewrite the proof inserting a new step 1, hey, call it step 0 if you like, that would say that we start with the right triangle as the given and you draw the altitude to the hypotenuse as your first step. So we're taking the shortcut though. So the given is we have right triangle ABC with altitude drawn to the hypotenuse as illustrated. We're trying to prove that a squared plus b squared equals c squared. We're trying to prove that a squared plus b squared equals c squared, c being the entire hypotenuse. So, to start with, our first step, let's start with the given. The fact that we have right triangle A, B, C with altitude drawn to the, and I'm going to abbreviate, oops, not B, H, hypotenuse. And why is that true? We have to have a reason for everything. The reason that's true is because, well, it is given. All right, from there, step 2. Oh, you're going to love this. You're going to love this. You're going to absolutely love this. Yes, you're going to love this. Because our next step is what I would call the obvious thing that you want to do with this diagram. Since the last section we looked at, section 8.1, you should just immediately, when you see this diagram, you say, hey, let's use corollary 1 or corollary 2. Well, the way I had this marked, you really can't use corollary 1 because I didn't give you a variable for the altitudes. We can't take the gentle dive. But we sure can use corollary 2. Corollary 2 saying this, that d over, say it with me, come on now, d over b equals b over the whole thing c. Of course, not only does corollary 2 say that, but corollary 2 also says, on the other side, E over A equals A over C. By the way, for those of you who are visitors to this YouTube channel and did not see section 8.1, you don't know what this is all about. But this is how we remember corollary 2. Corollary 2 says, when I have a right triangle, oh no, I forgot to mark that this is a right angle. There. When I have a right triangle with the altitude drawn to the hypotenuse, then this will always be true. I call it diving through the roof. That D, let's go over here, that D over A equals A over C, and on the other side, D over B equals B over C. That's corollary 2. Corollary 1, by the way, was the gentle dive through the triangle. Corollary 1 said that D over the height, H, whatever you want to call this, D over H equals H over E. That's the gentle dive through the triangle. But we're not using that one. We're using corollary 2. We're using this one. Oh, I forgot to mention just the beauty of what we've been doing. It's almost as if the entire first half of the book had the sole purpose of preparing us for this moment. All of chapter 7, similar triangles, leading up to being able to demonstrate that corollaries 1 and 2 must be true. And why do we have corollaries 1 and 2? Not so much that we can solve problems from section 8.1, but we have corollaries 1 and 2 so that we can use corollary 2 to prove the Pythagorean theorem. And there are many other ways to prove the Pythagorean theorem. I have posters. If I put them on here, it'd probably be a copyright violation. But I have some posters of, let's see, President James Garfield did a proof of the Pythagorean theorem. I have a poster of that. Who was the others? Leonardo da Vinci did one. And some of the guy whose name I can't pronounce did one. And there was another one, I've forgotten who it was. But I have posters of 4 people in history who have come up with their own proofs of the Pythagorean theorem. And I'm sure there are many others. So there are different ways to do this. This is one way, using corollary 2. So we're going to simply use corollary 2 and write down the facts here that D over B equals B over C. D over B equals B over C. And while we're at it, we'll put a semicolon here to say, here comes something else. On the other side, we have E over A equals A over C. E over A equals A over C. And why is that true? What's our reason for this being true? Well, corollary 2. This, by the way, again, is the only time in the entire book when I allow you to mention a theorem or a corollary or a postulate by number. In all of the cases, you have to either use a shortcut name or you have to write out the whole thing. But in this case, I do allow you simply to say corollary 2 is your reason why this must be true. Now, from there, we really don't need the diagram for the moment because we're going to do to this what we love to do with proportions. Yes, what is our favorite thing to do with proportions? Yeah, I heard like 3 or 4 of you say it all at the same time there. We will cross multiply. So statement number 3. Let's cross multiply this one. What do we get? And you got it. B squared equals DC. Let's put it alphabetically, I guess. CD, DC, it doesn't matter. Semicolon. We'll do the same thing here. A squared equals CE. Now, how do we know that's true? Our book calls it a property of proportions. Well, I'm a big fan of just telling it like it is. Why write a property of proportions? That's so unclear. We're simply going to say, what did we cross multiplied? It's true because of cross multiplication. Now, this is perhaps the trickiest part in the entire procedure, although I would not really call it tricky. It's the trickiest, but it's not tricky. And for this, let me just go to a blank screen here for a moment to remind you of something. In your Algebra 1 days, and for those of you who have had Algebra 2, again in your Algebra 2 days, you saw how to solve equations such as, how about x plus y equals 5 and x minus y equals 1. What do? You add the two equations. X plus x is 2x, y plus inverse y is gone, 5 plus 1 is 6, divide by 2, y equals 3, and if y is 3, x must be 2. you've got your solution to 3 as an ordered pair. Why do I mention that? Because why is it legal for us to add equations? Well, what I'm really doing is I'm taking this equation and I'm adding 1 to both sides. But on this side, I'm going to add another name for 1. What's another name for 1? Right here. 1 is also known as x minus y. So I'm really adding the same thing, because these are the same, to both sides of that equation. I add it in the form of 1 on this side. I add it in the form of x minus y on that side, but it's really the same thing. So I'm just adding the same thing to both sides of an equation, thus making the scales balance. So, back here. That is why I'm allowed to add these two equations. If I add these two equations, I would have a squared plus b squared. Ooh, it's getting close to the Pythagorean theorem, isn't it? Equals what? CE plus CD. CE plus CD. What did I do? I simply added the same thing to both sides of an equation. Do you remember what we call that? That is the addition property of equality. Addition property of equality. Remember, for every step in a proof, you have to have the reason why it's true. Now, oh, this is the fun part. Look right here. See anything kind of special about this? Oh, there's a C in both terms. Yes, there's a C in both terms. Can we factor that out? Yes, you can factor that out. We're going to factor out the C. You remember how to factor. If we've got CE plus CD, I can change it to C times, if I pull the C's out, what am I left with? E plus D. Please note, that's nothing more than the distributive property backwards. Instead of multiplying C times E plus D, getting CE plus CD, I'm reversing that process and taking the C's back out again. It's kind of like the distributive property is when we're having a test and I distribute the test to everybody in the room. I hand it out to everybody in the room. But then when the test is over, what do? I take the test back again and put it in a pile out here. And we're left with nothing but frustrated students sitting out there by themselves with no more tests in their hands. That's factoring. But I'm going to simply refer to this as the distributive property because that's the way the book does it. Instead of calling it factoring, we're going to call it the distributive property. So I'm going to factor this. Statement number 5. Bring down the a squared plus b squared. Then factor out or undistribute, take the c out. I'm left with e plus d. Why is that legal? It's nothing more than the distributive property. This equals that because of the distributive property. Distributive property. Actually, I suppose you would have to say it's a combination of distributive property along with substitution, changing this into another name for itself. But we're simply going to refer to it as distributive property. That makes it more clear what we just did. Now, here's the best part of all. See that E plus D? Go back to the diagram. What is E plus D? Yes! E plus D is C, right? These guys, this piece and this piece, have to add up to the whole thing. D plus E is C. Oh, so that means I can change this into a C. So that gives me what? C times C. And what's C times C? Oh, C squared. Yes! Step 6. We now have a squared plus b squared equals C times C, which is c squared. And the excuse that we're going to use, yeah, sometimes I call the reasons excuses. The excuse for that statement is substitution. We're just changing this into a better name for itself. Yeah, I know we could add in more steps and get picky and say that E plus D equals C because of the segment addition postulate, and then use substitution. But we're simply going to take a little shortcut and just say it's substitution. And we have, congratulations, we have proved the Pythagorean theorem. We have arrived at the thing we were trying to prove. By the way, I still find folks who, when they get to the last step of a proof like this, they say, the reason that's true is prove. The reason it's true is prove. What? Are you trying to tell me that that is true simply because we were trying to prove it? I could prove that the moon is made of green cheese if I just say, well, it's made of green cheese. Why? What's my reason? Because prove. Because I'm trying to prove it. That makes it true. No, this is silly. Don't ever put that word over there. That makes 0 sense. That word never belongs in the reasons column. Prove. Don't be ridiculous. The imaginary student still does that. And Mr. Peter, you're not being nice. I'm sorry, but you've got to stop doing that, imaginary student. You've been in my class for like how many years? Like 30 years? And you still haven't caught on that you can't put that word over here? Well, I'm just a little slow to catch on. Yes, I've noticed. But that's all right. I still love you anyway. Just hang in there. Someday you'll get it. I think maybe I have it now. I hope so. Substitution. And we have proven the Pythagorean theorem. Awesome! Yes! It's kind of sad that we have reached the pinnacle. And now we're on the way back down the mountainside. But as we go down the mountainside, let's pick up some speed and do even bigger and better things based on the Pythagorean theorem. First, we need to take a look at how to apply this stuff. What is it used for? All right, let's do a quick example. Let's use the same example that I used here on this thing. Suppose I have a right triangle, and suppose the legs are 3 and 4. On the homework, when I give you problems to do like this, if it's not obvious, like everybody by this time after having seen this, everybody should recognize that if these sides are 3 and 4, the hypotenuse must be 5. And that's legitimate. You don't have to show me any work. If I give you a right triangle with legs of 3 and 4, I would hope that you would instantly say, oh, hypotenuse is 5. Yes, no work to show. But let's do the work anyway to see how it would work when the numbers aren't so nice. If we have a 3 and a 4, what do? We start with the Pythagorean theorem. A squared plus b squared equals c squared. I will expect to see that on your paper. I will expect to see that on your paper multiple times. Every time you need to do a problem that requires some work, I expect to see the Pythagorean theorem at the top of the problem. So now we fill in the blanks. A is 3. B, Mr. Peter, what? How do I know whether I put the 3 there or the 3 there? It doesn't matter because it's addition. What's that special word that says it doesn't matter? Addition is the C word? No, not congruent. That's silly. Come on. No knee-jerk reactions here. Addition is commutative. And again, there's no N in that word. It's not commutative. That sounds like a communicable disease. No, it's commutative. So the commutative property says it doesn't matter where the 3 and the 4 go, as long as your hypotenuse is the C value. That's critical. These have to be the legs in any order. This has to be the hypotenuse. We're looking for the hypotenuse. 3 squared 9, 4 squared 16. 9 plus 16, 25? Yes, 25. If that's c squared, then what's c? C would be 5. We're done. That was easy. Let's do one that's a bit different. How about, let's try this. 6 and 8. Let's do it for 6 and 8. Now, some of you out there are looking at it saying, oh, Mr. Fair, if I just double the 3 and double the 8, would I also just double the 5? I didn't say that right. No, I'm sorry. I didn't say anything. That was the imaginary student speaking. Imaginary student. Be careful what you say. What you meant to say was, if I just double the 3 and double the 4, would I simply double the 5 and get 10? Yes. But let's do it this way, because it's not always that easy. 6 squared plus 8 squared equals the hypotenuse squared. 36 plus 64 equals the hypotenuse squared. 100 equals the hypotenuse squared. So the hypotenuse must be the square root of 100, which is 10. Yes, it does work. Let's see. Let's do an example that's considerably uglier. Consider this one. Oh, how about if we do 5 and 12? This one's kind of fun. Again, we start with the famous Pythagorean theorem, and this should be on your paper first thing. A squared plus b squared equals c squared. Oh, we haven't had a quiz this time yet. Should we throw in a quiz now? Nah, let's not bother with a quiz. We'll have a quiz next time. A viewing quiz. I don't want to do a viewing quiz every time. Have I done a viewing quiz with you guys yet? Yes, I think I have. Oh, by the way, I've never mentioned, the reason I'm wearing a tie today is I don't want you guys to forget what I look like in my regular school uniform. So for today, and maybe one more day, I want to look normal. Then I'll go back to my flannel shirts and my short sleeve shirts and stuff. But for today, yeah, let's look normal. All right, hey, you guys should try the same thing. Change into your school uniform so that you can feel normal also. So what do we have? We have 5 squared plus 12 squared equals c squared. 5 squared being, of course, 25. 12 squared is 144. Add those two, we get 169. Hey, does that number look familiar? 169? We talked about that one last time. Yes, we do know the square root of 169. C is 13. So if the legs are 5 and 12, the hypotenuse is 13. These, by the way, are some that the book writers mention on page 295 as being worthy of memorization. This could save you some time and trouble on the PSAT and SAT exams if you remember the 5, 12, 13 ratio in right triangles. That if the SAT exam were to give you a right triangle where the legs were 5 and 12, you don't even have to do any work. You know the hypotenuse has to be 13. Memorize that one. It's worth it. In fact, if this were 10 and that were 24, guess what this would be? Yeah, 10, 24. This would have to be 26. It works that way. It's pretty cool. Here's a tricky one. What if this were 2.5 and this were 6? This would be 6.5. As long as the ratio is the same. The other one that's worth memorizing and comes up quite often, even in real life, is 3, 4, 5. If you see a 3 and a 4, you know that's got to be 5. In fact, if you see a hypotenuse of 5 and a leg of 3, you can automatically know the other leg has to be 4. This relationship comes in very handy, by the way, in pre-calculus and trigonometry. We just went over these rules with the pre-calculus class just a couple days ago. It comes in handy later on. And we'll talk later about some real-life applications of how this can help you out in real life, believe it or not. Okay, let's do one that's even uglier than this, though. Suppose we have a triangle that doesn't work out so nicely. Suppose we have one that has, I'm just going to make this up, suppose this is 5 Suppose this is 8 and this is C. Let's see what happens. Let's see yeah, what happens. All right, so we have 5 squared plus 8 squared. I expect to see this written at the top of the problem as you work your way down. Equals C squared. Then we have 25 plus 64 equals C squared. Add these two, we have what? 89 equals C squared. So C is the square root of 89. What in the world do you do with that? Nothing. You're done. The hypotenuse is the square root of 89. If it's something you can't take the square root of because it's irrational, you leave it the way it is. And we could get an estimate of this. We know it has to be more than 9 because 9 times 9 is only 81. It has to be less than 10 because 10 times 10 is 100. So it's going to be 9 point something, 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 something. We could pull out a calculator and get an estimate. I don't care about your estimate. I do not want your decimal approximations. I want the perfect exact answer, square root of 89. One last thing before I give you the assignment, and that is this. What if we reverse the process? What if I gave you a 5 here, and suppose I give you I'll give you a 10 here. And we're looking for the leg instead. Let's call it A. Let's call it B, kind of be consistent. A, B, C, okay. Tradition, by the way, says we always put C opposite the right angle. That's mathematical tradition. All right, so with this guy, what do? We plug in what we know, and we solve for what we don't. But please, oh please remember, this is the hypotenuse, right? It's opposite the right angle. This has to go where C is. It has to. It's not optional. Then A is 5, and B is unknown. We now solve for B. How do I do that? Oh, no problem. Just go ahead and do this. 25 plus B squared equals 100. Now what? Oh, I know. Yes, you do. Subtract 25 from both sides. B squared equals 75. Therefore, what's B? B is the square root of 75. B is, therefore, the square root of 75. But wait a moment, don't stop there. Don't stop there. I just happened to have picked my number, so this comes out pretty cool because we can simplify the square root of 75. Surely there's somebody out there who remembers how to simplify the square root of 75. Yeah, you got it. We change that in our head or on our paper. Either way, I don't care. We change it to 3 times 25. Because we know the square root of 25, the 25 is able to, what's the word? Yep, I heard you. I even heard you thinking it. Yes, the 25 goes out and goes pa-ching, pops out, turns into a 5 on the outside, and we're left with a 3 on the inside. So the proper way to express the length of this segment is 5 square root of 3. And you're done. All right, I don't think it gets any harder than that. There are examples in the book. Actually, the book's examples, yeah, they do one with 3 and 7. You can try that one for yourself. And we're pretty much done here with the Pythagorean theorem. And next time, we go on to some other cool stuff about the Pythagorean theorem. And we are building up to, this is section 8.2, we are building up to another grand pinnacle of all geometry. In section 8.5, we're going to introduce trigonometry, which is awesomely cool stuff. I can't wait to get there. But we've got some other stuff to look at first. In the meantime, your assignment. Let's see, I will be posting this on Wednesday because I'm only supposed to be posting things on Monday, Wednesday, and Friday for this class. So I'll post this on Wednesday, which from my perspective is tomorrow. From your perspective, it's today. That's weird. I feel like I'm speaking to the future here. This will be due the next official class day, which will be Friday by noon. So the assignment I'm about to give you is due noon on Friday. And let's see what it will be. I don't recall. Do I have it written in here? No, I don't. Oh, no, I didn't write it down in any place. Pause for a moment if you want to. Or don't pause. Let it keep running. I have to look up the exact assignment that I have traditionally given over the years. And this is section 8.2. Geometry, there it is. Section 8, 2. And the assignment will be on page 292. Let's clear all this. Page 292, numbers 1 through 16 all. Let me take a peek at those and see if I like what I see. 1 through 16 all. Oh yes, these are nice. These are very nice problems. A couple of them are a little bit tricky, but hey, it's the tricky problems to separate the A's from the A pluses. There are a couple that are a little bit tricky. Some of them, if you see a diagram like this, for instance, where you're told that this is a right angle and this is a right angle, you just need to, in your mind, split it into a single right triangle. There are a couple like that, and don't let them trick you with these things. Oh, there's one where they give you this diagram and they tell you that this is 45 degrees. Well, if that's 45, guess what this has to be? 90, 45, this has to be 45. That makes this a 45-45 triangle, which makes it isosceles. And the other side, oh, they tell you this is also 45, and therefore, if this is x, this must also be x. And so that means, and then they give you this length here, which is 6 square root of 2. So if we just get rid of the unnecessary stuff here, what do we have? An isosceles triangle where the hypotenuse is 6 square root of 2. So what's that give us? A squared plus b squared equals 6 square root of 2 squared. Hey, how in the world do you square 6 square root of 2? We haven't discussed that. Let's take a look at how to square 6 square root of 2. 6 square root of 2 squared. Well, not hard, because all you have to do is square both parts. It's 6 square root of 2 times 6 square root of 2. So 6 times 6 is 36. Square root of 2 times square root of 2 is 2. We get 72. So this becomes 72. And here, what's x squared plus x squared? How am I supposed to know? Oh, come on, think your basic algebra here. 1x squared plus another x squared is, oh, 2x squared. That's right, because we've got 2 of them. Now we're going to divide by 2. You're going to divide by 2. I tell you, it gets lonely around here. I need an imaginary student. Mr. Pierre, is that like your imaginary friend? It's very similar. The 2's cancel. We're left with x squared equals 36. Therefore, x is 6. I just gave you the whole answer to number 12. Whoa, that's making life too easy. Okay, so 1 through 16 all, and you're on your own from there. Thank you for listening. Not that you really have any choice. And catch you next time.